Hello and a very good day to Dr. Adil and everyone. Today I will be presenting about the journal that I found, which is Numerical and Experimental Investigation of CI Engine Parameters Using Pump Biodiesel with Diesel Blends. This topic are related in the theme 1, which is Sustainable and Low Carbon IC Engine. And my name is Rexy Ronald Robert. My matrix number is 85544. So now moving to the next slide, the title is Addressing the Fossil Fuel Dilemma with Pump-Derived Biodiesel. Under the context section, it explained that fossil fuels are diminishing, transport account for 30% of global energy, and we urgently need to mitigate the harmful CI engine emission like CO, NOx, and HC. Under the fuel substitute, you can see that the pump biodiesel is great because it has a high yield of 5,000 kg per hectare and requires no engine modification. Finally, this study objective is to evaluate the biodiesel blends like B20, B30, and B40 experimentally and mathematically model them using response surface methodology, or we call as RSM. So for the next slide, which is parallel investigation, empirical testing meet numerical modeling. On the screen, you can see green boxes showing our experimental setup. We use two-stage transistorification process to make the fuel, tested it in a Kirloskar TV1 engine, and collected data using an AVL gas analyzer. Below that, the gray boxes show our numerical modeling using central composite design, which has a 30-run setup and RSM optimization. Both of these paths lead to the big box on the right, which is determining the ideal operational sweet spot. So now let's move on to the next slide, which is the first physical bottleneck, viscosity and filterability. Here, you see a bar chart measuring the FBT value, which show how easily the fuel flow through a filter. The dotted line shows the ASTM standard line of 1.38, and the B20 blends perfectly meets this limit at exactly 1.38. However, as the engine physics box explained, blends like B30 and B40 fails basic operational viability because sterol glucoside and thick consistency cause fuel line clogging. Now, let's move on to the engine performance balancing lower energy density with improved combustion. On the left side, you can see two graphs showing how the engine performs as we increase the load. The top graph shows the brake specific energy consumption, which basically means how much fuel energy the engines need to run. The green line shows that for the B20 blends, it, it is 11.52 megajoules per kilowatt hour, which is only 2.12% higher than the normal diesel. The bottom graph shows the brake thermal efficiency, which is how well the engine turns the fuel into actual power. For B20, it is very strong at 32.14%, which is just 1.96% lower than diesel. If you look at the Dark thermodynamic currents textbook, a text box on the right, it is explained why this happens. Biodiesel naturally has a lower calorific value, meaning it holds less energy, so the engine has to consume slightly more fuel mass. But because biodiesel contain built-in oxygen molecule, it is compensate for this by making sure the fuel burns much more completely inside the cylinder, keeping the efficiency competitive. Moving to the next topic, combustion dynamics, higher cetane number accelerate ignition. On the left, you can see a very clear drawing of a green fuel injector spraying fuel directly into the engine cylinder. At the bottom of this drawing is a timeline measured in milliseconds. As you read from left to right, you can see the ignition delay phase, followed by a green hill-shaped which represent the heat release. The dark box on the right, called combustion kinetics, explain the cetane advance. Pump biodiesel naturally has a higher cetane number than normal petroleum diesel, meaning it is highly reactive. Because of this, it has shorter delay, meaning it ignites much faster after it is injected. Finally, under smooth the heat under smooth heat release, it is explained that because of the fuel ignites earlier, the burning process is extended and much smoother. This is great for the engine because it is prevent sudden, violent spike in cylinder pressure that usually happen with biodiesel. For the oxygen advantage, significant reduction in CO, HC, and smoke. This slide shows three very large green downward pointing arrows which represent the exact pollution reduction for the B20 blends compared directly for standard diesel. The first arrow shows hydrocarbon went down by 6.12%. The second arrow shows carbon monoxide went down by a massive 17.67%. The third arrow shows smoke opacity went down by 9.0%. To understand why this happened, look at the dark box at the bottom title, The Chemistry of Complete Oxidation. Pure diesel often suffers from fuel rage zone in the cylinder area where there is not enough air, which cause partial combustion and create toxic black smoke. But pump biodiesel is an oxygenate fuel. Because the extra oxygen is built directly into the fuel molecule, the carbon is fully oxidized into carbon dioxide. This effectively destroys pressure and drastically lower and the toxic exhaust coming out the pipe. However, we also must discuss the downside of this thermodynamic penalty. Here you can see a line graph that goes very sharply as the engine load reach 100%. The orange box point that B20 blend produce 5.91 gram per kilowatt hour of NOx, which is 2.03% higher than normal diesel. If you read the unavoidable trade-off box on the right, it explains the temperature penalty, the exact same thing that reduces the smoke, which is the built-in oxygen rapid burning. Iris can cause the fuel to burn significantly hotter inside the cylinder. Because of this elevated peak temperature, inert and atmospheric nitrogen react with oxygen to form harmful nitrogen oxide or NOx. As the bottom text notes, this is a critical limitation of oxygenated biofuel. Solving the smoke problem inevitably make the NOx problem slightly worse. So now we can focus on uh, the next slide, which is optimization using RSM, which is called response surface methodology. Locating the optimal operational parameters. On the right is a 3D surface graph with a green target at the peak. Under model reliability on the left, we prove our maths that was highly accurate with R squared value greater than 0.99. The big green box highlight that the mathematical sweet spot. It reveals that the absolute best configuration is a 20% biodiesel blend at a 75% engine load. This specific setup gave an excellent desirability score of 0.97 out of 1.0. As the top right box explained, this exact point perfectly balanced everything. It maximized the efficiency while keeping the NOx temperature penalty manageable and staying below the physical filter clogging limit. So, for the conclusion, in the green strange verified box, we prove that B20 is a perfect drop in replacement. It, it keeps high efficiency while heavily reducing carbon monoxide and smoke. But looking at the red hard limitation box, blends like B30 and B40 are too thick and will clog the filter. Also, the 2.03% NOx increase is still an unsolved problem. Because of this, the Blue Future Research Scope box outline our next step. We need to test chemical additive to lower NOx and run long-term tests to check for engine wear. Thank you for very much for listening my presentation. Thank you.